Welcome. In this video, I'm going to walk through an example that relates to homework 9 on logistic regression. So I have a data set already in here, and let me just give you a summary of that. So I've got these variables y, x1 through x4. And again, you can take a better look at them. You already are familiar with making box plots, histograms, and so on. So if you want to do that, but let's just run an OLS regression here. And I'm going to just do summary LM. I'm going to do y as the dependent variable and regress it on all the other variables. Data is H09. And just here to pause for a moment on this y as the dependent variable, if you look down at the summary, and you can see the 5-number summary here for y, you might notice that the max is 1, the min is 0. That doesn't mean it's a dichotomous variable, but it does happen to be one. We could investigate that further if we liked, or if you like, you can check that in any given data set, but this is a dichotomous response. So with that in mind, let's go ahead and run the regression and check what we've got. R square is not especially large at 0.11. And look for statistical significance, and I see that x3 is close, at least at the 0.05 level. So significant at the 0.1 level, not at the 0.05, but it's close. X1 and X2 have quite large p-values, so this goes to maybe some other parts of the question that might be in the homework, interpreting p-values. So if I see very large values, 0.99, 0.85, that suggests they don't belong in the model, perhaps. These things, we aren't establishing that these coefficients are any different from 0, and if these coefficients are 0, then that says that x1 has no impact on the response, essentially. So there might be some questions related to that. Take a look at the homework and see, but just again, checking that you're interpreting the p-values over here correctly. All right, so the next thing is we want to run a logistic regression. So if our response variable is dichotomous, takes on values of 0 and 1, this might be the thing to do. So I'm going to do ML for model that's logistic. And here, instead of LM, I have GLM. And I've got Y as the response again, all of the explanatory variables in there. So I put dot there. And here, I have to do something a little different. So I type family equals binomial. And that line indicates that this is going to be a logistic regression. And then data, learn how to type, is H09. So run that. And then I want to see the output. So a summary of my model that's logistic, ML. And I get this as a result. Now, some differences here. Now the test statistics are Z values instead of T as they were before. Again, it shows the P values, and not surprisingly, again, X3, or at least it's not surprising to me, it's again close to statistically significant at the 0.05 level, 0.0585, so not quite, but close. X4 has a moderately large p-value, and then X1 and X2, again, quite large, definitely appearing that they don't belong in the model. But the rest of the output, there is no R square that is being provided. There's no F statistic, right? The output for the logistic regression simply looks different. So that's something to note there. There's a question about log odds, or maybe we want to interpret what the log odds are or see what that is. So what is the log odds? So Again, you might have to go back into the textbook, go back into the class notes, but we had the probability of success divided by 1 minus the probability of success. So that's the probability of failure. So the probability of getting a 1 divided by the probability of getting a 0. And then you take the log of that, because that thing itself is called the odds. Probability of success divided by probability of failure is the odds. And then take the log of that, and that's the log odds. So this relates to the mathematical equation for the logistic regression. So again, that's a little bit mathy. It's outside of R and just something you might look at. But what are these coefficients? These coefficients represent the change in the log odds. So if there's an increase in x1 by 1, so let's suppose that x1 increases by 1, that means that the log odds over here is going to decrease by 0.01163, right? This value here. That's where that's coming from. So that's how we're interpreting the coefficients here, right? So as x1 gets larger, essentially the probability of getting a 1 as a response does go down. The log odds decreases. So that's hopefully a little helpful in just thinking about what those coefficients mean. And probably takes a little bit of work looking at the equations, some practice, but hopefully it's again, just a little refresher there. So we want concordance and then also Somers D, right? These are two different measures of fit for our model, and they're going to involve some different packages. So concordance is in a package called survival. So that I already have installed, but, and then we'll put in concordance there. And this is going to take the model, so ML, that in there, and it gives me some stuff down here. Some stuff, be a little less ambiguous. It gives me the concordance value, 0.6831, and I'll get to that again in a moment. Let me get Somers D though, and then we can look at them, both those things together. So Somers D is going to be in a library called information value. So run that, and then I've got Somers D, pulls that right up. Now, if you're looking at this yellow bar here, it tells you what it wants, actuals and predicted. But let me just get an error message here for fun. Let me just suppose I did the same thing that I did with the concordance a couple lines above, because I actually have done this sometimes. But let's just suppose we're typing that in. You didn't see what the yellow bar said, or you forgot what maybe was done in the lectures, so on, and you just try to run this and you get an error message. So you come down here and you look at the error message, and it says error in concordance actuals and predicted. So it doesn't have a predicted in here. So what do you need? Well, you can type in help Somers D, but what we want here are actuals. What are the actual values? They're the H09 Ys, and we want the predicted scores. So here I'm just going to use predicted, say. So predicted are going to be then the fitted values from our model ML. All right, so let's do that. And it gives a Somers D of 0.366. So now just a little note on, again, the concordance is 0.681, Somers D is 0.366. They're related. So let's just walk through how we're getting the concordance, or where that's coming from. So got 416 concordant pairs, and that means that when the two observations. So we take two observations that one is a 0 for y and one is a 1 for y. And then we look again at the predicted values. And if the predicted value for the observation that takes on a 1 is greater than the predicted value for the observation that takes on a 0, we say that's concordant. Right? We were expecting the observation with a higher predicted value to be more likely to be a 1 than the observation, and it resulted that, in fact, it was a 1 and the other one was a 0. Discordant, so let's divide this though by, again, that same 416, and then we had discordant pairs, 193 of them. What are those? Those are the cases where the observation with the higher predicted value was actually the 0, and the observation with the lower predicted value was actually the 1. So it turned out the opposite of what we might have been expecting. So here's just what's the ratio of the concordant pairs, where we got what we were expecting, to all of the pairs. And so let me just hit that, and it gives you 0.683087, which is the same, except just rounded, as 0.6831. Obviously, this one's being rounded at the fourth decimal place, but they're the same number, right? That's how this is getting calculated. Okay, how is this related to Somers D? Well, let me just copy this little piece out here, put it down here. And Somers D just has this little distinction. Oops, let me get back here to the beginning, is that it takes the number of concordant pairs and subtracts the number of discordant pairs here in the numerator. Then I hit enter, and what do I get? 0.36161741. It's the same number as up here, right? That's what that's doing. All right, so that's a measure of fit, right? The larger the number, the better, right? It means more of the pairs are concordant. They're lining up with maybe our expectations. All right, this next thing says find the G statistic. So again, there's no one command in R that will give you the G statistic. And the code for that is a little bit involved, as it were, or it's a bit to type in all over again. So I'm just going back to the R code from the lecture note that's available in Canvas, and I'm just going to paste that in here as opposed to typing it in all over again. I'm going to have to make some changes to it, but instead of typing it all, this is a case where I just want to copy paste. So I'm just going to paste that in there. Okay. So again, go back to the particular lecture in Canvas and find it there. All right, so just get this out here. So I want to find the G statistic. So it says it's a chi-square with p degrees of freedom. What's the log likelihood with all coefficients 0? Okay, so just benchmark there. So my data set here isn't SOL. That was in the lecture. And so I'm going to change the SOL to H09 and do that there and there. If I did that everywhere, then I could just run that and get the value, the log likelihood when the coefficients are 0. And then I can change this out here to H09, get the log likelihood for the fitted model. Again, so I need to change the name of the data set, H09. The model is not M1 like it was maybe in the lecture, but ML. And change that over here also, ML. And so now I can get the log likelihood for the fitted model. And then I'm going to get the difference down here. So I need to again change the name of the data set, H09. H09. So actually these are the individual values, so they have to be added up to get the full log likelihood. So there's this summation in there, so just to clarify that. So run that, and then the G statistic is 2 times the difference in the log likelihoods. So get that, and get that value 11. Don't know if that's exactly large or small. I'm going to skip this line here. I just want to get down to the p-value, give me an idea about how big is 11. This one has 4 degrees of freedom because there are 4 explanatory variables, right? There was x1, 2, 3, and 4. So just run this through, and I get a p-value of 0.0244. So fairly small. So it looks like the model is providing some explanatory power, and that jointly those variables x1, 2, 3, and 4 do belong in the model. Again, we can look back at the output for the model and suspect that maybe that's coming mostly from x3 in this case. All right, so now let's look at finding a predicted probability. So for that, you can use the actual model and the coefficients, and you could type out the equation if you go back to look at what the equation is. But let's just create a new observation here in a data frame. So data frame, and let's just assign some values to x1. For this purpose, let's just go ahead and go back and look up at the summary for the data, the 5-number summary, and look around, eyeball around the mean. Looks like maybe values of 10 are okay, right? So 10, maybe let's just go with things like that. So let's say x1 of 10, x2, let's just say it's 10 also, x3 is 10, x4 is 10. So we have this new observation. Great. And now let's go ahead and get predicted values for a predicted value for that observation. So let's go with predict, and we want the model that's logistic. We tell it what the new data is. It's going to be this new obs, short for new observation. And I'm going to choose type is response in here to get the estimated probability. And it shows up down here as 0.4781. So here, when you had the ordinary least squares model, maybe you didn't need to worry about this response option here, but let me just illustrate part of the importance of that. Let's get rid of it and see what this does. So it shows now negative 0.0875. What is that? Well, that's the log odds, if you will. So what I'm going to do here is down in the down here in the console, I'm going to type in the equation for getting the logistic probability. So it's 1 divided by 1 plus E negative that equation of the betas times the x's. So the beta hats times x's. So it should be negative 0.08. So in other words, just 0.08, right? So I just can copy this in. I'm going to ditch the negative sign because it's negative times negative makes it a positive. And then I know what result this is going to give me, right? This is going to give me the 0.478. Right? So I just hit enter, and sure enough, it gives me the 0.478, just like this. So that hopefully illustrates what the difference is between using response here and not using response there. So hopefully that helps. It's just an additional set of examples working in R to run logistic regressions and get some of the corresponding output. And hopefully that just gives a good jumpstart for working through again with some homework problems.